Hello, in this module we are going to calculate two relative breaks using R. Relative breaks is one of the widely used tool or indicator adapted in epidemiological study, where it is computed based on populations or individual having exposed with respect to individual having non-exposed. Basically is calculated as ratio. For example, we are having a populations, and in that populations few individuals are having cancer, and we want to find out that smoking is influencing for cancer or not. So, for all individual we can make two group, one as cancer present and another one is cancer absent. Now, another group we make from the same populations, those are smoker, and another group those are non-smoker. So, from those people who are smokers can be called as exposed to smoking. Among these smokers, how many are having cancer with respect to among the non-smoker, how many are having cancer. If we get the value and make the ratio, it will give us the relative risks. Mathematically, based on the empirical relation, it also mentioned that relative risks is mostly suitable for study where we are going for cohort, where we are having huge number of population where sample size is quite high. In that case, relative risks is most suitable indicator to find out the effect of exposure on disease in comparison to non-exposure for disease. In this module, we will see on functions that has been taken from R bloggers to illustrate the application of relative risks using R. Preparing data to measure disease frequency we will see here, function to compute relative risks we will see here, and statistical inference about relative risks on the example data we will look. So, the reference is here. So, for details on relative risks, now we are going to function to preparing the matrix. So, this is the first important function need to be carried, because in relative risks we have to prepare the contingency table. Once we prepare the contingency table, after that we can do the analysis. So, to preparing the contingency table, this function matrix is used, where 63, 916, 568 and 1258 are basically these observations in first row, first column, first row, second column, first column, second row, and second row, second column observations. So, here number of observations taken into total number of row as a 2, that is why in row equals to given as 2, and column matrix is defined as disease and control. So, we are having two column here defined as disease and control, and name of the rows are defined as exposed and unexposed. So, once we define this call names of my matrix as disease and control, and after that row names of my matrix as exposed and unexposed, and after that once we put the print of my matrix, result will be like this. So, first column, first row, and second column, second row are like that. So it's a typical contingency table, 2 by 2 contingency table. So this contingency table will give us the results about relative risks. Now later on we will go to functions to calculate the relative risks, but before that I would like to state about something about relative risks. Relative risks is a ratio of the probability of an event occurring in an exposed group to the probability of the event occurring in a comparison to non-exposed group. This event may be stated as the developing a disease or being injured. So here in this example we are considering the developing a disease. Disease can be anything. So that probability of that event, that is disease, in exposed group to the probability of event of occurring in comparison to non-exposed group can be obtained through the relative risks. It includes two important features. One is comparison of risks between two exposure, puts risks in context, and second one is exposure here is ensured by having proper denominator for each group representing the exposure. So relative risks is basically probability of event when exposed by probability of event when non-exposed. Here we may think one example where the probability of developing lung cancer among smoker was 20% and among non-smoker 1%. If we prepare it in a table, then 20 out of 100 divided 1 out of 100, that is 20 will be the relative risks for developing lung cancer for smoker. It can also state like smoker would be 20 times as likely as non-smoker to develop lung cancer. The alternative term of relative risks is called risk ratio. It is sometimes used because it is ratio of the risks in the exposed divided by the risks in the unexposed. As an alternative of relative risks, we will see absolute risks will come in another module. Now we will coming for the functions to calculate the relative risks. This function is taken from the R bloggers. Here the function is defined as calc relative risks, where functions of my matrix is considered, where my matrix is basically the 2 by 2 contingency table, and alpha is considered as a 0.05, and the reference row is considered as a 2, because it is very important to mention the reference row for calculating the relative risks. If we here, since we are referring the reference group as a 2, so whatever the relative risks will obtain, it will be based on this in comparison to second row. Row names here is given as my matrix for I equals to 1 to number of row, that is we are having total 2 number row, and later on disease unexposed as defined as my matrix as reference row 1. So in this analysis, whatever relative risks we will calculate, that will be basically for disease exposed group with reference to disease unexposed group. Now like earlier slide, control unexposed is defined as my matrix for reference row comma 2, and if I equals to reference row, disease exposed follows to my matrix of I comma 1, and control exposed is given as my matrix I comma 2. Total exposed is basically the disease exposed with total control exposed, and total unexposed is the disease unexposed in addition to control unexposed is defined here. Now probability of disease given exposed is defined here as disease exposed given total exposed, and probability of disease given unexposed defined as disease unexposed given total unexposed. To calculate the relative risks, probability disease given exposed by probability disease given unexposed is used to obtain this final relative risks. Now this whole calculation we will call as print paste of category row name relative risks as relative risks. Now in addition to the point estimates of relative risks, another important is this confidence interval. So several times we do see that relative risks comes more than 1 or near to 1, but based on that point estimate we do conclude that the relative risks is higher or lower respective study design. But in addition to the point estimate of relative risks, it is very important to consider the confidence interval of relative risks. If confidence interval of relative risks comes within the value of 1. That means if the confidence value somehow touch the value of 1, then it can be stated that the relative risk is equal to 1. So both group, that is exposed and unexposed, both are having equal risk for developing the disease. Once it is not, it found that it is not, confidence interval is out of this value of 1, then we may make the statistical inference that one group is having higher or lower relative risks in comparison to other. So that is very important to be considered for statistical inference about the relative risks. Here these functions is there to calculate the confidence interval. Confidence level is defined as 1 minus alpha multiplied with 100, and here sigma is defined as square root of 1 by disease exposed minus 1 by total exposed plus 1 by disease unexposed minus 1 by total unexposed. So theoretical formulations for to obtain the confidence interval we may seek in book, and here sigma is the standard error to estimate the log of relative risks. Now to get the z value, basically to obtain the p value, here it is saying that z is equal to following normal distributions with 1 minus alpha by 2, and lower value of relative risks is defined as exponential of minus z multiplied with sigma, and upper value is defined as relative risks multiplied with exponential of z multiplied with sigma. The whole matters is printed as spaced category row name confidence intervals. So as a result, when we explore this analysis given earlier, and this is an exposed reference group, we will see the results how it is coming. Now the results is there to calculate the relative risks. Relative risks is my matrix comma alpha 0.01, and once you put these first functions into our console and enter, then we will get the results as 0.20. So here in our example, our data was like 63 among exposure were having disease and 916 among control were having exposed, and among the disease people 568 were unexposed with the disease and 1258 were control, those were also unexposed from the disease. So this table shows that about total exposed people, that is 63 plus 916, among them only 63 were having exposed and disease, whereas among the unexposed, total unexposed people, that is addition of the observations obtained in the second row, that is 568 plus 1258, only 568 were having disease. So it shows that unexposed somehow is having higher chance of being disease in comparison to exposed. So here we didn't take any real life example, but in real life examples some exposing factor may be good for having not disease, or that exposing factor may be preventive for in that disease. Here in this example you are also getting that exposing factor is preventive for the disease, and as a result we are getting that confidence intervals coming 0.14 to 0.28 with point estimate of relative risks 0.20. So it shows that relatively it is only 20% of having chance to having disease among the exposure in comparison to those are unexposed. So in real life example, maybe these consumptions of olive oil may be protective for myocardial infections. So people having exposed with or consuming olive oil having lower chance of disease, that is myocardial infections. So it can be interpreted or linked to the real life example as well, but it's not that always relative risks will be like lesser, sometimes it may be one more than one. So there are so many ways to interpret the relative risks. Relative risks is used to frequently in statistical analysis for binary outcome, but the outcome of interest has relatively low probability. It is thus often suited to clinical data where it is used to compare risks of developing a disease in people not receiving the new medical treatment or receiving a placebo versus people who are receiving an established or standard care treatment. Alternatively, it is used to compare the risks of developing a side effect in people receiving a drug as compared to the people who are not receiving the treatment or receiving a placebo. It is particularly attractive because it can be calculated by hand in a simple case. It is also useful amenable to regression modeling, typically through Poisson regression modeling. In a simple comparison between an experimental and control group, a relative risk of 1 means that there is no difference in risks between the treatment groups, and relative risk less than 1 means the event is less likely to occur in the experimental group in comparison to control group, and relative risk greater than 1 means the event is more likely to occur in experimental group in comparison to control group. So, here we have taken disease and exposed that can be also altered as cases and control, and the same kind of relative risks can be interpreted. As a consequence of delta method, the log of relative risks has a sampling distribution that is approximately normal with variance that can be estimated by a formula involving the number of subjects in each group and the event rate in each group. It permits these delta methods to construct a confidence interval which is symmetric around log of relative risks. It is to be noted that relative risk is a standard score for chosen level of significance and a standard error also. The anti-log of relative risk can be taken for to obtain the log of confidence interval, giving the high and low bound for an asymmetric confidence interval around the relative risks that we have seen here. It can also be used in regression modeling concept. In regression modeling, the treatment is typically included as a dummy variable along with other factors that may affect risks. The relative risk is normally reported as calculated for the mean of sample value of the experimental variables. In this module, we have seen the function to calculate the relative risks, and we have also find out the confidence interval for points estimate of relative risks. When we are having some assumption to perform the relative risks and compare with our confidence interval obtained from the study sample, we can make the inference that relative risk is really higher or really lower or equal as of our inference. I hope these functions and these illustrations can help you for further applications of relative risks from real data.